Hi, this is Elkin for Technaid Research Digest. This is a podcast where we talk about cutting technologies related to exoskeleton and motion capture system. As a research and technology company, we're interested in knowing new and fascinating research, especially from our partners or colleagues. This time we have the opportunity of speaking with a PhD student from Miguel Hernandez University of Elche in Spain. I have the pleasure of introducing Laura Ferrero. So, Laura, welcome to the podcast.
Hi, Alkin. Thank you so much for inviting me. I'm really happy to share, our experience with all this technology. And well, I think it will be very interesting, this talk.
Great, great. That's awesome because we're really interested in knowing people like you. Working with the exoskeleton, with the H3 in this case, with another approach. I mean,
hmm
uh, especially for me, it's really important to know what's your work. So, what about if we start knowing a little bit about your background? Why do you start
Okay.
researching? Can you tell us?
Yeah. Well, it's a bit, it changed a lot. The path I follow. I studied biomedical engineering in the University in Valencia, in Polytechnica. Then at the end of it, I decided to go more into research because at the beginning I was not sure about it. So I did a master in data science in the Polytechnic University in Madrid and also in the Netherlands in Eindhoven. And after that is when I decided to do a PhD because I was really into research and especially into brain computer interfaces, which is something I learned 3 years ago. I didn't know what they were, and that's when I just moved to back because I was living in the Netherlands. I was doing my internship in Philips, and then I moved back to my city, Alicante, and I started my PhD in the University of Elche.
Great, that's awesome. Yeah, data science, all this part of machine learning. It's a really good tools. You have learned a lot of things. Now you can bring to your PhD. So, what's your subject? What's your theme in your PhD?
Yeah, well, I think I need to speak about my lab first. My lab is called Brain Machine Interface System Lab. They work
Okay.
with everything we do there is focused on brain computer interfaces. Like in general terms, they are systems that use the signal of the brain to control any kind of external device. The external device can be the screen of a laptop, can be a wheelchair, can be a treadmill, and can be exoskeleton. Like your exoskeleton is the one we are using. And my part or my work there is focused on motor imagery. So we plan to use this kind of interfaces for people who have motor limitations, and we want them to control the exoskeleton by means of their brain or their brain. So what I ask them is to imagine that they are walking without actually executing the movement, just the imagination of it, and with this imagination, we have a system that captures it and translates this information to the exoskeleton. So it moves when the person is imagining, and it doesn't when the person is focusing on something else. The main goal there is to define a new kind of rehabilitation therapy for people with spinal cord injury. So more or less, that's the main idea of my PhD.
Good. That's awesome. So I have one question. I want to understand a little bit more. What kind of mind states are you handling? There are a few, two, three states because you said you ask to the patient to imagine, but only there is only this state, or there are another.
I don't really get your question. What do you mean by stages or
You can be relaxed, imagine
ah?
what kind
Yeah.
of.
Okay, now I get. Yeah, so our control right now is really basic because we want the exoskeleton. The exoskeleton can perform different movements and can have different speeds. But right now, since we are starting to use it, we want to just control the start and stop of the gate. So we
Okay.
ask the person to imagine when he wants to, or when he or she wants to start the movement, and we ask the person to be relaxed for stopping the movement. So it's like two tasks we ask them to do, so for having this kind of control.
Okay, I see. So like initial conditions for the experiment.
Yeah, yeah.
I see,
Also,
I see, I see.
the importance of motor imagery, it's because it has been studied that when a person is imagining a movement, if we think about the brain, there are some changes that are really similar than when a person is doing real movement. So the brain patterns that are produced are really similar. That's why we really want to focus on this kind of imagination instead of asking the person to think about anything else. And also based on this imagination, we kind of want to promote a mechanism that's called neuroplasticity. This mechanism is something that our neural system has when we have an injury, that it kind of recovers the pathways that were broken, for example, in a spinal cord injury, and kind of it's good for rehabilitation in general. So with this motor imagery thing, we ask the people to do, we promote this mechanism.
Okay, I understand. So, how do you get these motor images? I mean, I can
Yeah.
imagine you're using EEG signals, but what's the procedure? I mean, how do you
Okay.
start with this?
Yeah. So for recording the brain signal, there are different techniques, but right now we are using EEG, that for brain computer interface is the most used one because it's non-invasive. There are different other techniques which are invasive, but they need a surgery. So ours is, as you said, you were correct, is EEG. So we place a cap on the participant with some electrodes that they measure this brain activity. And then for we have when we do it, we record the signal. We are seeing it in real time in a screen where I can see all the signals the way they go, but it's difficult visually for me to see when the person is imagining something because it's not that easy to get information from EEG. So in that case is where I apply kind of machine learning techniques that they extract features to discriminate between different brain tasks. And right now we kind of get information about the frequency of the signal, the power of the signal, and also something called kind of the distribution of electrodes, like how different brain areas connect with each other. Because something that changes when we are thinking about something or when we are thinking about something else. More or less, that's what we do.
Okay, I see. How many classes are you using? I mean, I presume you're classifying some signals, right? Some stages. How many classes are you using?
Okay, so for the control of the device, right now we have just two. As I said, we have this motor imagery thing and relax. So for motor imagery, we ask the participant to imagine the movement of walking. So they have to think about two legs doing this walking movement. And for the relaxing period, we ask them to be as relaxed as possible and kind of, I tell them normally they have to meditate. So they have to focus on their breathing or on their heart rhythm. So they have an abstraction from the everything that's around them and they don't think about anything else. And those are the two classes we want to differentiate.
Okay, I see, I see. So you detect, I mean, in your classifier, your methodology, you detect when a patient is relaxed, and when detect the intention of movement, you start controlling the exoskeleton. Yeah,
Yeah.
something like this.
Yeah, but I have to
Awesome,
add something
awesome.
on that because the
Yeah.
intention, I mean, there are some labs other research centers that they work on the intention. So just for starting, you have this task and you use it to start. But in our case, we need the person to perform this motor imagery continuously for keeping the movement because
Oh,
this
okay.
the main idea is to have it for rehabilitation. So we want the person to do it during a period of 20 seconds but continuous, So the exoskeleton will be walking as far as the person is doing this imagination. When the person stops, the movement stops.
Oh, okay, I see. It's really interesting because neuroplasticity it's the key there to
Yeah.
detect where is the damage in the brain and try to detect in the other part. Am I right?
Yeah, yeah, yeah. Sure. Totally right.
Great. Yeah, great. That's awesome. That's really good job. And I have another question with this because uh, that's one part, no? I mean, how to detect, get the signal, that's one process. But how do you use this with the patients and the exoskeleton? How to deal with wearing the exoskeleton, wearing the helmet? What's your experience with this? Because I think you're working in some projects
Mm-hmm.
and you have to take some data from patients, and that that could be really complicated. Or what do you think? So
Well, yeah, it's challenging to work with patients because we have a lot of things to do. As you said, we have to put the cap on the person, we have to put the electrodes, we have to see that the signal is being recorded well, but also they have to wear the exoskeleton, and for patients, we need to help them to wear it because they cannot do it by themselves. And we collaborate with a hospital in Toledo, which is for people who had suffered a spinal cord injury. And we have done some experiments there. Normally in our lab, what we do is when we design a system, we first test it on able-bodied subjects, so people from the lab. I do it myself as a user. And when we have several tests and we know everything is safe, everything is under control, and we can have a good experiment, then we translate it to the hospital and we test it with patients. So at the beginning, the first time I did the experiments with patients, I was really scared about it because I mean there was a lot of things we had to do, and also I wanted to do it fast because patients when they are in the hospital they had so many treatments they have to follow, and I didn't want them to lose their time. So that's challenging because we have to, for having the EEG recording, we have to apply some gel between the skin and the electrode for having a good connection and we can record the signal well. And also for adjusting the exoskeleton for each person, it's difficult because we need to change the sizes. We want them to have it fixed, and they also, and we need also to help them to work with it because at the beginning it's weird for them having the exoskeleton. At the end they get used to it, but that's something we have to manage in a very short period of time.
yeah, that's another really important part. In the same way you train your signals, the way to imagine, you have to train how to use the exoskeleton. I mean, even for us, it's really complicated to train how to use and transmit this for our patients. Probably it's complicated. So, what's your experience with this, in this training with the patients?
Yeah, well, I have to say that sometimes people who are able-bodied find it more difficult to work with it than patients. Something I was really surprised the first time I found this. And well,
Yes.
normally before, yeah, yeah, I think for able-bodied, since you can completely move your legs, having them moved by an external device, you find it more strange than patients that they cannot completely move them. So at the end, the exoskeleton is helping them, and for them, it's not that rare, let's say.
Wow,
And yeah.
I didn't see that coming.
And
Yeah.
well, for us, for the experiments, what we do, because I cannot ask a person to the same day perform these two mental tasks at the same time they are learning how to use the exoskeleton because that's too much, and we learned that that's too much for a day. So now what we do is we have kind of a preview session just with the exoskeleton. So we adjust it to the user, and we train a bit the balance, the way they have to move, we have what's the best speed for them. And when that it's okay, they feel safe and secure working with it, then we can move to the experimental session in which we combine it with the EEG recording, the brain task, and all the control.
Okay, I see. So yeah, step by step. First with the EEG, and then with the exoskeleton, and then combine it.
Yeah,
That's a lot of work, both for you and for the patient.
yeah.
Yeah,
I was really surprised because in this hospital, patients are really motivated. Sometimes I'm more tired than them at the beginning of the experiment because
yeah,
they are really
I can figure
enthusiastic
it
about
out.
this technology.
Yeah, and what do you feel the experience of the patient using the exoskeleton? They feel comfortable. They feel, yes, we want to use. What do you think with this?
Well, the majority of patients really like to use it because when we do the experiments, there's always somebody behind them, so they are holding them so they can feel safe. And some patients they use crutches so they can support their walk. And there are if they want to, there's always also somebody in front of them. So one person in front of them, one person behind them, and also they have the crutches for additional support. So the main idea there is to have them feel that they are safe, they cannot fail. And when we have that, they start to walk, and most of them in 10 minutes, 20 minutes using it, they can walk perfectly.
Wow, so fast!
Yeah.
Wow, that's awesome. I didn't know that. But yeah, because I have some doubts about how to use in your experiment, because the XOH3 is more like an assistance, not sorry, it's more related to rehabilitation than assistance, because we
Hmm.
expect people to start using, and after some sessions recover some movements, partial or complete, also based in neuroplasticity. So maybe in some experiments it's really complicated because it's really lightweight, but in another kind of experiment, the good part is our exoskeleton is lightweight. So in your case, it totally worked. You made
Yeah,
it. You can use it.
yeah, sure. We with patients all the times we use it. We just had the problem once. Then a patient, it was a girl. She was really scared about falling because she last time she fall, she had this spinal cord injury. So it was more this time that time was more difficult for us to make her feel comfortable and safe with it. But in the rest of the cases, in 10 minutes, 15 minutes of usage, we normally get it. Because when they
Wow.
feel there's somebody from behind who is controlling completely, because the person who is behind the exoskeleton normally controls the balance that we want to do during the gait. And the person in front is just there for support. So they feel like they can do it. And as far as they balance more, they can walk better and with further steps.
So it's a really good team you have. I mean, not only working, you also are working with physical therapists, also with mechanic engineers. I mean, how many guys are you? Are
Well,
you biomechanical engineer?
what about the rest?
Can you tell me?
So
Yeah.
yeah, in the lab in general, most of them we are engineers. There are electronical engineers. There are computer scientists. Also, there are psychologists because for this brain part, in which we ask them to perform different tasks, there's this background. And there are also physical therapies, but when we go to the hospital, in the hospital in Toledo, there are three or four that help us with everything to help the patients to balance correctly, to move the legs correctly. How should we wear the exoskeleton in which position, standing up, sitting? They help us with all this procedure.
Hmm. Great, great. So, are you? I mean, you're telling a lot of about this hospital, the hospital from Toledo. Are you working in another project with them, or
Yeah, well,
related with
right
your
now
PhD, or?
Right now it's the same project. It's a national project called Walk. So we have it when I started my PhD, I enrolled with this project and it's going to finish next year. So during all this project we are working with this hospital and we plan to have two different new projects with them too.
Oh, okay. And you are trying to continue using the exoskeleton and brain interface, or what's the next step with this?
Well, it's a bit of everything. Yeah, we want to keep with the exoskeleton and the brain computer interfaces, but we were also thinking about spinal cord injury stimulation as an additional technique for this rehabilitation.
Oh, okay, I see. Directly activation to the patient. Oh,
Yeah,
that's great. That's great. Okay, I see. I see. I have some questions. I remember you received some training to use the exoskeleton to work with this. I think you're using Bluetooth interface because you're using a high level control. I mean,
yeah,
you're using an internal walk pattern, and you start with after processing and detecting the intention, or sorry, the
imagination.
imagination of the patient of walking. How was this experience? I mean, do
Well,
you think the training was good with this? In the high level, it's enough for your task?
okay, so for this training, it was my colleague, the one that did the training, and then he translated all this knowledge to me. And well, we found it pretty easy. As you said, we use high level, so we don't control anything in the gate pattern. We just send a command that says start the gate or stop it, and we change also the speed, but that's all we do. We focus more on the EEG recording and processing. And yeah, that was pretty easy. We use MATLAB as the software for developing our interface, and with MATLAB, we directly created a Bluetooth connection with the exoskeleton. And from there, we just send the commands, which is a number that says start, stop, change speed. And that was easy for us to just integrate this software with our system.
Okay, I see. And do you about this biomechanics in the patient? How you feel this gait? This trajectory, it's good. You think we can improve it? What do you feel in your experience with this? Because you're modifying the speed of this gate. Maybe I don't know the reason why you're using only this. Why
Well,
you're using the speed? You're modifying the speed, right?
Well,
Or
I in my experiments I don't. So
okay,
in other experiments that we do in our lab, yes, we change the speed. But in mine right now we are using the lowest speed because
okay,
for patients we want them to start as slow as possible. Then maybe for the future we think about something differently. But right now we just use the slow one. And speaking about this gait pattern, well, in general, the only thing that I see is that sometimes we need to balance a lot. So for the steps to be normal, otherwise they are really short and patients feel like they cannot go ahead. But that's
okay. I
something also
see.
good because it teaches them to perform this balance because at the beginning is the physical therapist the one that's helping them or us from our lab forcing them to do this balance from one side to the other when they are walking. But with training, at some point, they are the ones that start to do this balance that helps them to walk.
Okay, I see. Yeah, because one really good thing about this gait pattern, it's not like humanoids. I don't know if you have seen humanoids. How does it work? Because those robots doesn't have hips, so they don't have this kind of balance. So they perform a really high hip movement and then perform the step.
Okay.
Our gait pattern is more like a human pattern where you need to create this balance. Maybe it's
Hmm.
not easy at the beginning, but after some tries, you patients can learn how to use it and maybe recovery better. We suppose the gain pattern.
Yeah, well, that depends on the level of it, the injury that the patient have. Some of them they have they have a strong, I mean they have strong legs, although they had the injury, so they can really control this balance. But some of them after the injury they don't have strength to do that. So I think for those, the last ones, it's more difficult to do this balance, and they need more time to, or more time, or more support from behind to do this gait.
Okay, I see. Have you tried the assistance of the exoskeleton
Yeah,
in
we are
your?
using, we are the whole time we are using the assistive mode of the exoskeleton, so they just.
But I mean, the you can vary the percentage of assistant if you want
Ah,
10
okay.
to 100 percentage. Yeah.
Yeah, sure, but with patients we only use 100% of assistance
Ah,
because
okay, I
they really
see.
need it.
Okay, I see. I mean, maybe in another projects, they are testing how what's the experience of the patient giving less or more percentage of assistance. And I'm
Well,
not, I don't know.
yeah, well, I think as a for a long-term therapy, it makes sense to change it because it can start with a higher level of this assistance and then go down. But in my experiments, they are 1 week duration, so I don't have time to train this amount for having it lower. But I think, yeah, for future, it really makes sense that patients at some point they have lower level of assistance and they have to do it. They have to do the movement. They have to apply some effort on it.
Okay, I see. Awesome. Could you tell us a little bit about your results in your experiments? I
Yeah.
don't know. What do you find? What do you think?
Well, based in brain computer interfaces, most of the literature is focused on the EEG recording when the person is completely static or sitting or with a virtual reality, but not in movement. I think right now maybe there are some others that work with interfaces in movement, but not many. So as I found that, for example, for this EEG recording, it works best when the person is not moving at the beginning of the experiment. But then when the person is moving, it's more difficult because this movement introduces some noise into the signal. So maybe the thing I want to find, this brain pattern, I cannot see it because it's surrounded by noise, and which it makes it more challenging. And also another thing that I found really interesting is that it really changes from person to person. There are some users that are really good at modulating their own brain signal between the tasks, and we can easily distinguish between these two, the imagination and the relaxation period. But there are others, it's more difficult to see it. And there are some papers that say it's not a matter of the, it doesn't mean that they do it wrong. Is the only thing is that the EEG cannot see it. Because I mean, for example, they could be doing it perfectly, completely concentrated, but maybe the EEG has some limitations and we cannot see it. The main limitation that the EEG has is that we are measuring on something on the surface of the skin, and the motor cortex, and especially the part that is the work with the legs, it's really deep in the brain. So it's something that from a surface electrode is difficult to see. Sometimes we can, but sometimes there are some limitations with the technique. And I think the third conclusion we got, it's something that doesn't seem real, but it is. The motivation of the person, it really affects the performance of it. We see that when a user is not motivated because, for example, maybe the experiment was too long for them or they didn't get the result they were expected, it only gets worse. But when a person is getting good feedback, they like what they're doing, it gets better. So it's something we are trying to work on it. What to do to encourage patients to be motivated the whole time.
Wow, that's a really good conclusion. I mean, I was thinking about this because in some hospital, in some therapies, uh, physical therapists are telling, let's go, you can do it, you can do it. And sometimes we didn't see what's the impact of this, but yeah, all the rehabilitation, all the lessons, all learning, it's improved with this kind of behavior. So what you found, that's amazing. That's amazing, and really good. You can share with the community this kind of finds. I mean, I'm really glad you're working with this, and you can share with us this kind of projects. Uh, I, I want to congratulate you and your lab, because we think it's really interesting what you're working right now, and as future work you have a huge field to fill.
Yeah, thank you so much. Yeah, by the way, we have so many things right now. After each experiment, I have some things or some feedback. Okay, maybe for future experiments, I will think about this, or I will try to make sessions shorter, or I will try to give feedback or kind of gaming in case we have them motivated. So yeah, every time we have some new ideas for future projects, and we have a huge field to implement them.
Sure, maybe you can continue working with this brain interface, maybe with another kind of machine learning, another approach, with another kind of classes. I don't know. There are a lot of work to do there, and you're getting a really good experience with this, proposing these projects, how to join the a lot of parts of the science. I mean, biomechanical, rehabilitation, machine learning, brain computer interfaces are some parts that are working but not together. But now you're
Mhm.
starting with this, so that's really good.
Yeah, I really like when there's somebody new in our lab that has a different background because they really add something to us. Like for example, the new people that have arrived to our lab, they are psychologists, and they give you a perspective that you never think about. And that's something for us it's really interesting because when all of us have the same background, at the end we only see the same things or we find the same limitations. But maybe somebody new they can give you a new view. For example, something it's just an anecdote. Something we found in our experiment for the control, we have kind of a fixed period. So we had, for example, 10 seconds in which the user had to be relaxed, followed by 20 seconds in which they had to perform motor imagery, followed by another 20 of relaxation. So ideally, if the exoskeleton was well controlled, it would be static during the relaxation period, it would start moving during this motor imagery, and then it would stop again. And some users, even some patients from my lab and from the hospital, told me that since they know that the next task is going to be motor imagery and they are expecting it, they cannot be relaxed. At some point, they say, "Okay, we are knowing this is going to happen. It's going to happen," and then our system detects that they are not relaxed and they are starting to imagine the movement of walking, although we didn't ask them to start this period, and the skeleton starts to walk before the time we want it.
Mm.
So that's something we found really interesting. And they told me, yeah, I know I started it before time, but it was my fault because I knew the next task was going to be motor imagery, and I was expecting it, and I could not be relaxed. I just could think about my legs. So yeah, that's something we are taking into consideration for future experimental designs.
Oh, that's really good to know. That changed some part of the experiment, the protocol, perhaps.
Yeah.
You're improving this. That's really good. Uh, I have another personal question, let's say, more related with your machine learning procedure. Maybe
Hmm.
how do you detect? I mean, you're getting the EEG signals, and then uh, you
Okay.
extracting features, or what are you doing?
Well, it's kind of a traditional machine learning approach. So after we get the signal, we filter it. So we want to remove the noise introduced by the power line. We want to apply different frequency filters. And we also remove the contribution of the eyes, because when we blink or when we move the eyes around, there's a noise that is introduced as an artifact that we can see in the EEG signal. So we've cleaned that. Once we have the signals cleaned, then we apply some feature extraction methods. It's my third year of my PhD, so I have tried so many different methods, but I can divide them in categories, kind of saying. So
Okay.
one part is more focused on the frequency, because when we are doing a movement, or when we are imagining it, there's a rhythm that appears on the EEG signal, let's say, and it's in the frequency band that we call alpha and beta. It's around between 8 and 12 hertz, and between 14 and 19, more or less. It's variant. So in this frequency analysis, we try to find these rhythms that appear during this motor imagery, and we get the power of the signal at these frequencies. There are different techniques to get this information, like wavelet decomposition, Stockwell transformation. There are different methods. And the other approach I'm using, it's more about spatial information. So we want to get the covariance matrix of this data. So let's say how each electrode it's connected, let's say, to the rest, how the signals that are measured are similar. And then this information is the one that I extract to see maybe this is the spatial pattern that happens for motor imagery, that these areas are more similar, and then there's a completely different spatial pattern when we are relaxed, for example.
Okay, I see. And
And
do you
that's for feature
find,
extraction.
yeah, and do you feel, what do you find? Better with the frequency or with the space? Do you find some
Right
weights
now,
in?
right now I just changed from to spatial features, because right now they are giving me in my experiments the best results. And in the
Okay.
state of the art of BCI for motor imagery, those are the methodology that are mostly being used.
Okay, I see. Yeah, yeah, yeah. That's really good. So after this extraction feature, you have I don't know how.
Classification.
Yeah, directly to classification. How many features did you get?
So for these spatial ones, 32.
32. Okay, I see. And after this, a classification process. And what are you using for this classifier?
For a classifier, we use or support vector machines or linear discriminant analysis. And
Okay,
the
really.
thing we do is, instead of having the whole signal, taking it all, filtering it, and having some results, we want to do it in real time, because we want our system to give a decision in half of a second. So in half of a second, we want the system to say the person is imagined or the person is relaxed. So the exoskeleton it starts the gate or it doesn't. So we kind of take periods of half of a second of the EEG signal, and we perform all the steps I just said. And then for the new half of of the signal, the same, and continuously. That's the process we do.
So you have an independent sequence of the time series. I mean,
Yeah,
you, for example, you detect in this window relax, and the next could be imagine. So,
yeah.
but in time are independent. Okay.
Well, there's an overlapping, so we have, but yeah, then so
Yeah,
there's
yeah, yeah.
if we have a window like this, then we have a bit of overlapping, but they are moving, and yeah, they could have completely different classes between. That's why also we want this continuous motor imagery, because we want the person to be cognitively involved during the whole time. So maybe in these 20 seconds that I asked the person to perform motor imagery, there are in some windows that a person was not focused, because it's super difficult to be whole time thinking about the same thing. But in mostly of the time, the idea is in the mostly of the time they are doing it.
Okay, I see. Yeah, because I think it's a classic problem or sequence to sequence classification. where you have a time-related activity, like when you are running and you're using a watch, and you detect now I'm running, now I'm resting. That's a sequence-to-sequence classification. That's a really good
Yeah.
approach with this kind of problem. But yeah, it works. Super vector machines, the king in this in these problems.
Yeah.
Yeah, it
Yeah.
solves all. Good. That's all my questions I had about your project. Thank you so much for attending today. Uh, we expect having you in another opportunity and talk about your new projects. Thank you so much for attending today.
Thank you so much, Talking. It was really interesting. I really like our talk. We could discuss so many things. And yeah, I'm looking forward to seeing you again and keeping working together. So thank you so much. It was really nice.
Thank you. Have a good day.
You too.